Okay, guys, this video deals with assumptions for linear models. It's from Math 5500. And as we saw in, whoa, I don't know what happened right there. Okay, as we saw in class, actually just yesterday, that a linear model has some certain features. And the features, as we examine the scatter plot over x and y, if we can imagine x having certain factors, let's just call it x1, x2, and x3. And this would certainly continue. For each of these factors, there is what we call a mean response. In each of these observations here, there are certain assumptions that we have to consider. Now, if you would imagine this not being just generic x and y, but let's say that x is equal to an ACT score, and let's say that y is equal to maybe a first year college GPA. And let's say that we were examining the relationship between the two for all college students, entering college students, let's say, for, in the state of Ohio. So what we would do is we'd, be interested to see if their ACT is a decent predictor of their first-year college GPA. Well, a linear model is something that we may consider using in that situation. So if you think about an ACT score, for example, of 24, there's going to be some mean response. If we imagine that, kind of tilt your head sideways, okay? There's going to be some mean response. There's going to be some mean first-year college GPA for all of the students who score 24. But there's also going to be some variation. There's going to be variation within the distribution. So, we don't expect every single person with an ACT of 24 to all end up with 3.0s. In their first year of college. But, first of all, we know there's other factors that would certainly influence that. So anyway, we call this sampling variation, and this leads very nicely into a discussion about assumptions of our models. And what I intend to do in this video is, first of all, go through the assumptions, and there are 4. And then I want to go pull up a kind of an arbitrary data set and run through the assumptions. It's going to be kind of cool because I don't know what I'm going to find. And I'm just going to tell you as a researcher what I would look for if this was something that I was going to examine and potentially publish. So guys, remember our linear model for our population can be thought of as the mean responses for y as the sum of beta 0 plus beta 1x. Okay? So this is for the population. So enter into the picture the concept of errors. Very, very, very important in statistics. Examine the errors, examine the variability within the errors. This leads us to this form. But what we have to appreciate, this is not only true in general, as I've stated it right here, this is true at each data entry, at each data point, x1, y1, x2, y2, the data that we've collected. So I can come in with a notation and I can say any y sub I. Let's just say y sub 2, for example, can be created by taking beta 0, beta 1 times its x sub I. But as we discussed back previously, we don't expect every single one of these x sub i's to end up at the mean. So we have to include the error for that particular point. Because again, we're not going to create our mu sub y's for every single observation. Every kid with the ACT of 24 is not going to have a 3.0 GPA. There's going to be error within our model. All right? So our errors, I promise you I can spell errors. E sub i's, something I want you to think about these things is they are sample based. We examine errors from the data that we've collected, which is typically a sample. However, gang, we know that from a population perspective that our errors are going to follow a normal distribution with a mean of 0 and a variance of sigma squared. Also, our errors are going to be random. Now, if our errors aren't random, then that tells us a lot about our distribution. It tells a lot about the appropriateness of the model that we've selected. Well, in our case, we are examining because it sets the stage for bigger, better stuff. We are examining linear models. So what I want to do is I want to run through the 4 assumptions that we need to be able to validate before running a linear model. So the first one is linearity. And this is just pretty much a straight line condition. Now, I'll get into this a little more. I'm going to break each one of these down into separate pages, but I want to talk about the assumptions more broadly on this page right here. The next thing we talk about is independence, and I'll talk more about that. The third thing we have are equal variances. And the fourth thing we have is normality. Okay, now let's break these down into individual components. So very first, what do I mean when I talk about linearity? Well, you say, well, it looks like a straight line. Well, it does, but it's obviously not that simple. I would strongly urge you to get rid of the eyeball test, because the eyeball test can be very deceiving. So there's more sophisticated diagnostics that we can use. First thing I want you to be aware of is a really important plot that we can examine to look at linearity is between x and the residuals. Now, because our residuals can be positive or negative, I need to draw the line down like this. Now, if we get a residual plot that's completely random, no discernible patterns, kind of like a shotgun blast, it's kind of a violent metaphor, but then we can assume linearity. There's another plot that we want to look at from time to time, and this one is over our predicted values. Actually, I should say our residuals over our predicted values. Now, many times these are going to look the same, but there are certain times that these things will give you different plots, and certain times that this one can be more advantageous to examine. Now, things that we want to look for in these plots are, first of all, randomness. And what I mean by randomness is I want no pattern. Sometimes in these plots you get patterns like this. That's a big red flag. That's a situation where you know right off the bat that you have a linear model that's not appropriate. Another situation you get that gives you some issues, something like this. Now, something like this, I call this a fanning out or fanning in, depending on how you want to look at it. And that shows me at each one of these x values that the variance isn't the same. So that's a red flag for the equal variance assumption. Okay? All right, number 2, independence. Independence is the hardest one hardest assumption to validate. But the things I like to do here is just, again, look at a scatter plot of most likely the predicted values over the residuals, and just really examine this and make sure that there's no discernible difference from a random pattern. Another thing that you can do in independence is just make sure that your data has been collected in some random fashion. Guys, the third one we talked about are equal variances. And let's just bring in a big old fancy name that or fancy terminology that we're going to talk about quite a bit. And we're talking about homogeneity of variances. Guys, homogeneity of variances really is just a big fancy word for saying equal variances. Now, a threat to equal variances would be if I go back to my original drawing here. If I have a certain factor, maybe let's just focus on x1, where I have a mean response, which will be on the line. But let's say that the variation around that point is much wider than it is for this point. Well, then I don't have equal variances across the errors for each factor of the independent variable. And it's an important assumption that has to be validated when running a linear model. So again, the best way to look at this is to plot your residuals over your predicted values, and you want to see equal vertical distances. If you're a researcher and you see that, noticing that these vertical distances are all the same approximately, then that's good stuff. That means that the homogeneity of variance assumption has not been violated. However, if you, like I showed you on the previous screen, if you look at your y-hats over your residuals and you get a fanning out or fanning in, then that shows that for this particular value of our predicted, that the vertical distances are not the same. Down here, the vertical distance is not the same. So this would be a threat to this assumption. As the fourth assumption is the normal population assumption. And what we do in the normal population assumption, or at least the way that I think about it, is we assume the errors kind of around the idealized normal linear regression follows a normal model. And again, that just says that at one of these levels, back at x and y, at one of these levels, let's call it x1, where we have a mean response, that we're not getting into some wacky distribution. That actually looks kind of like a mustache, doesn't it? Okay. This just assures us that we are examining each distribution at each level of x under a normal model. And guys, this is very important for us when we get into inference, because we need this to assure that we are able to use a t-distribution. Now, the way to examine the normal population assumption hasn't been violated, I like to do two things here. I like to look at a histogram of the residuals. And if I get something like this, there's no reason for me not to think that this didn't come from a normal distribution. However, if I examine my residuals, and I get something like this, then that's kind of questionable to me whether or not that distribution of residuals came from a normal distribution. So guys, over here I would question that the normality assumption has been satisfied, because my residuals don't appear to have come from a normal distribution. So again, the normal population assumption may be violated. There's another way to do this. It's called a normal QQ plot. And I'll show you how to do this on R. And a normal QQ plot starts out with the standardized scores. So our standardized residuals. And it examines, well, easy for you to say, it examines these over the residuals. And what happens is we draw a vertical, or a line, think about just y equal x, and we plot these things. Well, the closer these points are to this line, the better the normality assumption is being satisfied. However, if we start, and let me put this in another color, maybe it'll help make it come out. If we start getting a lot of deviation away from this line, then that's an indication that our normality assumption is not satisfied. So we want points really close to this vertical, or this diagonal line. It's not a vertical line, if the normality assumption has been satisfied. So in the end of the day, guys, are assumptions ever violated? Assumptions are violated all the time. But what you want to ensure, and when we run through these four assumptions, linearity, homogeneity of variance, independence, and normality, we're going to see that probably some of these are slightly violated. Slight violations are okay. Except for independence. Statistically, violating the assumption of independence can rock your world. What happens, we can still calculate p-values, but our p-values aren't stable, and they give us very, very biased results. But slight violations of the other three, homogeneity of variance, normality, and linearity, it can be violated slightly, and we're okay. So let's oh, I don't know. Let's just get into the process. I'm really kind of shooting from the hip here. The process, and I'm going to demonstrate this on R, but the process is kind of like, really, it always reminds me of which came first. Yep, the chicken or the egg. And of course you can drive yourself crazy with conversations like that, right? But what actually is kind of strange about the process of conducting a linear model is we need to actually conduct it first so we can create our linear model, which ultimately creates our residuals, which we can examine before we really start our model. So we've almost got to create our model before we start it. So that's kind of why I always think about which came first, the chicken or the egg. So first thing I would do is I would create just a simple scatter plot over X and Y, and I would eyeball it. Does that appear linear? It does to me. Now, I'm not ready to end the game. There may be situations where I look at a eyeball something. That's not even a function, but let's look at something like that. Well, you know, you don't have to have a PhD in anything to realize that a linear model is not appropriate there. So this is a clear no. This is, well, my dogs are going crazy as usual. Imagine that. Even though this passes the eyeball test, to me it's still a maybe. Okay, so second step, fit our model. To create two things. I want my errors, which again is just a fancy way of saying residuals, and I wanted my fitted values, which are the y-hats. So I want to create those two things. Now, what I want to do from these is I want to examine this plot, and I want to examine this plot. What am I looking for? Vertical distance is the same, no patterns, or no fanning out of the residuals. I'm going to put that right over here. I don't want to see that. That's a clear threat to the equal variance assumption. Okay? The next thing I would probably do is I want to check for outliers. And this is as simple as getting a box plot for X and for Y. Now, if I have an extreme outlier, then I'd probably want to run two models. And my two models are one with the outliers and one without the outliers. All right, gang, the final thing, if we get a situation and it passes the scatter plot test, looks okay, residual plots Looking okay. The next thing I would want to do is I want to examine the residuals. Okay, what I want to do here, create a box plot. Oh, shoot. Create a histogram. Hoping this thing looks like it came from a normal model. And the second thing I want to do, create the normal QQ plot. If everything passes all these tests, I'm going to proceed with the inference. Now, it's a good point. Let's say you go out and you collect some data on 10 observations. Whatever they may be. And the goal of what you're trying to accomplish is just to describe these 10 observations. Then you know what? Eyeball it. Create your slope. Create your... Yeah, you're not going to do any inference. You're not conducting any inference. Don't worry about the assumptions. But if you're taking these 10 people and generalizing to a larger population, then the assumptions have to be satisfied. Okay, let me illustrate this. I want to get into R, and I've got a data set again, have on the desktop, and it's called income. And we'll bring up income and see what it looks like. So this is going to be a good practice to get things going on R. So first thing I would do is I would get my working directory, because I don't know what it looks like here. And you can see that it's users ddar bro, but I have my data on the desktop. So I want to set the working directory to be on the desktop. Next thing I'm going to do is I'm going to go get my data, and it's easiest to do the read CSV. So I've already changed the format of this file in Excel to a CSV form. And trust me, if you don't get it right, R will let you know really quickly. Before I do anything, I'm going to attach the data. Sometimes people forget that, and they run their means and their standard deviations, and things go wacky, and they start losing their mind, going crazy, and wondering what happened. Always go ahead and attach it. Now, I never look at this, but students always like to look at their data. So you can see here that we have 80 observations, and it looks like this this data set has something to do with income, and I'm assuming these are probably in thousands of dollars. And this is education, so I'm assuming that is probably total education from first grade. So this person right here only has a 9th grade education. Looks like this person has 7 years additional education beyond high school, so probably thinking a master's or so. It looks like there's also a categorical variable here. I assume that stands for black. I assume this is Hispanic, and I assume this is white. Kind of makes sense. Okay. So, what would I do? The first thing I'd want to look at is I'd want to look at the eyeball. And let me back up. Remember the hashtag. Let's say the goal is to predict education. No, let's not do that. Let's predict income from education. So guys, the income is going to be our Y, and education is clearly going to be the X. So the first thing I'd want to do is run the plot of education, and let me see, how do we code that? ED and INC. Okay, it's going to be easy to remember. So I want ED and INC. And I get this, and again, I haven't worked this problem, so I don't know what I'm going to find. So it's kind of cool that we can just kind of talk this through together. I haven't even looked at this. I see some linear tendencies, but if I draw a line down the middle, I mean, there's some there's with the eyeball test, there's some concerns. That's not the classic linear. It's not the classic scatter plot that would be well fit for a linear model that we see in textbooks. So actually, I'm really glad that I chose this one. Okay, the next thing I'd want to do is I want to fit my model. So I'm going to call it model, and I'm going to go LM. Guys, I always have to put my Y first, tilde, and then put my X. I really don't care about the intercepts and the slope at this point, but I just really want to create the model. Okay. Now, once I fit the regression, there's two things I want. I want my errors. So I'm going to be creative here and call them errors. And the function on R that we do to get our errors is called resid. So I take the residuals, R-E-S-I-D, of my model, and I've stored it as errors. Now, if you're like someone who likes to see stuff, just type errors and you see there's our residuals. Now, for example, this observation number 4 has a residual of negative 13.66, which tells me that their observed value is 13.66 lower than their predicted value. The next thing I'd want to do is I'd want to do the fitted values. So the fitted, and actually it just turns out this is fitted. So if I do my fitted, you can see that I have those. Okay. Now I want to get into a couple of different scatter plots. The first plot that I want to examine my X, which is education, over my residuals, which I've called errors. Now, got some issues here, don't we? Because when we look at the level of 8, 9, 7, there's not as much variation as there is when we get on out in this part right here. Notice the variation here from about 18 all the way up. It's probably the level 16 that concerns me the most, and the level 14 that concerns me the most. So I clearly seem to have kind of a pattern, and I have evidence of this fanning out. So you guys tell me what we got on our mind here. I'm starting to question whether or not a linear model is truly appropriate. And I'm starting to really question whether or not our homogeneity of variance assumption is holding true. But I'm not going to go crazy. I'm going to go ahead and look at some other stuff. So I want to look at my fitted values over my errors. And in this situation, it looks like I get to essentially the same thing, and I have the same concerns. Not going to do anything rash just yet, but a little concerned. Now, next thing I want to do is look for outliers, and this is of the original variable. So in education, we have a nice, pretty symmetric, no outlier distribution. But I am betting that it doesn't hold true with income. Now, we've got some skewness going on here with income, and we've got some outliers. We've got some people, making a significant amount of money compared to the rest of the people in the sample. So I may consider one of two things. I may consider some sort of transformation on income. So let's do a transformation, and let's do a natural log of of income. Oh, okay. R just uses log. Now if I do a histogram of, well, a box plot, I've kind of smoothed out my distribution where I have no more no more outliers, but it's a trade-off. If I don't include income in my model, but I include the natural log of income in my model, well, that's a little bit harder for people to understand. We know what an additional dollar means, but what does an additional $1,000, additional $10,000? But what does an additional log of income mean? Well, it's just harder to evaluate, but it sure does help us in taking a look at our assumptions and see whether or not they're violated. All right, I'm going to go on with the original model. So, let's assume that we passed the scatter plot test, which we really didn't. The next thing I'd want to do is look at a histogram of the residuals. And I see no threat to normality here. It's a little positively skewed, but there's no reason for me to believe that this couldn't or probably didn't come from a normal distribution. Now, the next thing I want to do is I want to look at the normal PP plot. And this is probably the most effective way to examine the normality. So what I need to do first of all is I need to standardize my residuals. And I'm just going to call that STRES for obvious reasons. We do that by what's called the R standard. And what that's going to do, it's going to give me the standardized residuals for all of my residuals. So remember, when you standardize something, you divide by the mean and you subtract the mean and divide by the standard deviation. And when you standardize something, you transform it into a model, a normal model, which has mean 0, standard deviation 1. So if I take the mean of my standardized residuals, then I should get something pretty close to 0, appreciating rounding issues. If I take the standard deviation of my residuals, then I'm going to get something probably pretty close to 1, which we do. Now, what I want to do now is I want to come in and get a picture. And the prompt in R for that is to go QQ norm of my model. And now we'll do colon here and execute something else called QQ line for my model. Maybe. Because I want the diagonal line as a kind of a reference, a comparison for my points. Now remember, if these points, okay, this is fun. What's going on here? I called it model. Oh, no, I did it wrong. This should be QQ norm of the standardized residuals. And then QQ line of the standardized residuals. First mistake I've ever made, guys. Yeah, right. Okay, we're pretty close to that line. But when we get up here in the higher end, we get a lot of deviation from the assumption of normality. So, so guys, at the end of the day, what would I do? Yeah, I don't know. My options are really pretty simple. Option number one is go ahead and run my model and report the results, but indicate to the reader that there's a possible threat to certain assumptions. The certain assumptions that I'm most concerned about are the normality assumption. I'm sorry, the equal variance assumption, and the linearity assumption. The normality assumption from the QQ plot, there's also a mild concern for that. So again, what I could do is go ahead and run my model, report the results, and make sure I report and provide pictures and graphs and scatter plots and things that let someone determine whether or not they're going to believe my analysis. The second thing I could do is run another model with education as my predictor, but what did I call the I did a transformation okay, I could do TRANS as a function of education. Now again, the problem here is oh guys, I'm losing my mind here. Here we go. The problem here is what? We're taking education and we're predicting not income, but the natural log of income. But if we do our errors, so we'll call these errors 2 because we're doing a second attempt at errors, and we look at the residuals of our model 1. And then if we look at our, what do we call it, predicted? No, just call them fitted, okay? So fitted 2 is our fitted model 2, model 1. Now if we look at a plot of our original X, which is education, on our errors 2, I'll guarantee you we're going to get a better scatter plot there. Better in terms of less variation, more across each level. The vertical distances are more consistent. We don't have that fanning out approach. And let's go in and look at the QQ plot just for the heck of it. Okay, so let's call these a standardized residuals 2. So it's the second one. So I want to do, let's see, R standard of our model 1. Hope you guys are keeping all this straight. And then we want to do QQ norm of STRES2. And I want to do QQ line of STRES2. And guys, you can see that we take that up here, that wacky variation we had at the very top. We get a very, very nice QQ plot there indicating that we have normality. So, you know, we've got to make a decision here, and there's going to be a trade-off. We are threatening the assumptions. We are violating the assumptions, in my opinion, if we don't do a transformation. But if we do a transformation, things appear to be more stable. Okay? So guys, that's the end of this video, and you know, you're going to see this stuff again. So have a good one.